Hi everyone, welcome to our presentation, Development of a Real-Time Decision Support System for Generating and Laying Irrigation Schedule Forecasts. My name is Nicholas Kiggundu. I'm here with Aloysius Mobangizi and Joshua Wanyama. We are from Makerere University, Kampala, Uganda. And I'm going to ask Aloysius to take us through this presentation. Over to you, Aloysius.
Thank you so much, Prof. Chigundu. Okay, the world population is projected to be 9 billion by 2050. And this means we have to close a gap of growing food between the food that is produced and the one which is needed, which is almost 70%. Rice has become a staple food for over 50% of the world population, and most of this is grown under continuous flooding. And this water used accounts for 40% of the irrigation water use, and this has become a global concern. So various studies have been in combining water saving practices with decision support systems to see how water can be saved, and most of the studies have yielded success. So though we have a challenge, a problem, that the existing decision support systems for paddy rice cannot automatically integrate irrigation and weather forecast information and deliver it to farmers. And the farmers end up irrigating by emotion. So this means they do not know how much and when to irrigate. And this results into under or over irrigation, and of course, low water use efficiency. So the objective of this study was to develop a real-time mobile phone application, zone support system, that generates weather and irrigation schedule forecast to end users so that we get to contribute to efficient water utilization and management in rural and rice production. Then the specific objectives, the first one was to design the real-time mobile phone application, support system that generates irrigation and weather schedule forecast to farmers and extension workers, and also to test the decision support system in the rice production system. So the study considered the design considerations that guided the development of the system. And among these included user-friendliness of the interface, because farmers want the simplicity of the design, and the alternate wetting and drying practice, water management practice, which is currently in use in many parts of the world. Then the robustness of the algorithm, because the farmers or the algorithm had to be capable to handle the farmers as a group or as a scheme. And then the ability to generate real-time information to the farmers. Among others, also there was versatility to be used in diverse areas, so different parts of the country and on the world, and also capability to integrate crop information with the rain. If rain is estimated to be coming up, then it suspends irrigation schedule. So the design approach involved the web tier system where the admin has to log in, and this can be a farm manager or irrigation scheme manager. Then the business tier logic, which integrates the web tier system with the data tier and the back-end information. And then the data tier for storage of information, and then everything is relayed in the computer web system or on the mobile app, which is the tool that the farmer uses. And then all these links to the weather online application programming interface that is helping in relaying this information of the forecast. So the weather API is connected, and the farmer information is registered in the database. And then we have the background task that queries the latest weather information from the Weather Online API. So the return information is used in the FAO Penman Monteith equation, the water balance equation, combined with the alternate wetting and drying with the crop environment to be able to determine how much water and when it is needed. So here we're able to calculate the volume and time to irrigate, and then issue commands to the farmer, which we can also log as information that can be retrieved for use. So on objective 2, there was testing the functionality of the student support system, and this we had to check the soil type, so that this soil is part of what goes in the back end of the tool, and is used to calculate the water moisture content, soil moisture content. Also, the irrigation parameters were determined, and the canal was estimated at 55 meter cubed per hour. Then the study used the probe access, the probe access holes to use the soil moisture sensor to measure the volumetric water content of the soil every time we wanted to measure it on a daily basis. And we made sure that irrigation was always was not going beyond 40% of the available water. Then the soil moisture content measurements were taken and compared with what was forecast by the tool. And all this was again checked with the model evaluation methods using bias, root mean square error, model efficiency, coefficient of determination, and Wilmot agreement index. And this resulted into the following result, where we have the mobile app as a tool displayed with the login interface, the menu page, and the current day's irrigation schedule. And here is a screenshot of the computer web system that feeds into the mobile app. And it has the characteristics of the information that of the farmer that is input into the tool. So when you look at this table, it shows the ability of the tool to carry out forecasting and send information to the farmers in different locations with the crops at different stages. When you look at the irrigation regime and growth stage, reproductive, terminal, vegetative, and flowering, all can be checked, and information can be calculated and sent to the farmer differently and in different locations, as you can see on the parameter location, where we have Nakri, Nakawa, Kajansi, and Ujiri, different locations. Then the commands are also issued, where we have the no irrigation and others, depending on what the stage of the crop is at. So as a result of the observation between the forecast and the soil moisture measurements in the field, the observed and forecast soil moisture content in the irrigation scheduling were found to be closely following the same trend. And this was evaluated in the model and the model evaluation. And the root mean square error was 0.55, 0.055, which was small. The bias was 0.115, and the coefficient of determination was 0.99, close to 1%. The model efficiency also was performing close to 1%. The agreement index was 0.99%. So here it showed that there is a strong agreement between the forecast and observed values. And looking at this, the model was accurate, almost close to the observed. So the conclusion, the study showed strong relationship between the forecast and observed irrigation schedules. This study has demonstrated that high-rise decision support system is a valuable approach for farmers organized as individual groups and scheme level, depending on the size of the scheme, but it can have a high number of farmers entered there. Then we have the high-rise forecast. It does a 7-day forecast for the farmer, so a farmer has not to worry about the number of about what is coming up. If they know they are not going to irrigate, they don't have to fight for the water. Then the study will also help the farmers and other users in efficient water management in rural and rice production that has since been taking a lot of water. We recommend that further development of high-rise irrigation decision support system is done to increase the capability on data storage. Currently, the information generated is so high, and cloud computing can be explored. Then investigations on how much water is saved versus the continuous flooding, and then integrating this decision support system in the government development programs, and further studies on also on this system on how it can be used in other crops, because it can work also in horticulture and others. We thank the partners that supported us in this project, and we thank you so much for your attention.